Yeah, I'm so excited. Okay, so my name is Camille. I am the Internal Vice President of Space Technologies at Cal, or STAC. I'm a third year in Industrial Engineering and Operations Research. And this is our second and final info session for fall 2017 recruiting. Please sign in your attendance at this URL if you haven't yet. I see some people reaching for it, so I'll leave it up there for a second, but it's a bit.ly stack-info, so just let us know that you're here. Okay, so I'm going to read this slide to you. This is what you're going to get to learn today. The first thing is why space, that kind of general why we're interested in space, who we are, our projects. We're going to go into a little bit more detail into each of our projects so that when you fill out the application, you can say which one excites you the most. And then we'll get into the external, kind of our advisory boards, our industry partnerships. We're kind of a unique club in that sense. Get into expansion, and then final remarks, which will just be an overview of the application process. So welcome. Hope you have fun.
Cool. My name is Travis Bashirs. I study engineering physics here. I'm a junior. I guess I also do econ. Just a quick background of my background. I've worked in space on laser technologies for the past 4 years, and so you might see a couple laser things come up in our slides. I'm one of the co-presidents. So I just wanted to give a really good intro on what's up with space right now, because it helps define all the projects we're doing and the tractions that you may hear about in the news. So this is just a nice plot that shows the cost to launch 1 kilogram of mass into low Earth orbit. And so this is the whole rush to going to the moon, right? It happened the cost got pretty down, but then back in 1990 the cost skyrocketed because we now started skyrocketed. That's pretty good. I didn't even see how it coming. It skyrocketed, and then it re-entered. Okay, but so this was basically when we relied heavily on Russia. And then it started to come in a few U.S. companies and other companies in Europe, and it started to fall down. And then SpaceX came in, and now the cost of launch is going down a lot. And so when the cost of launch falls to low Earth orbit, it enables a whole stack of things to be worked on. Also, another pun. If you think of this as the launch market, right? And this cost is falling down, the cost for each of these things also falls. And so we're trying to hit almost all of these verticals with all of our projects. And just a cool note is that $13 billion has been invested into space startups since 2000. So this is just if you look at these different sectors in the new space startup world, this is kind of how they break up in the different industries. And these are all new companies. And you can kind of see over time this is kind of happening. So one thing we really do in STAC is try to talk to the majority of these companies to see what they are working on and to see what problems they've kind of encountered. And so if you think about companies, they have to go after cost-driven efforts. They can't really do research-based work because it doesn't get them money. So we talk about that with them, and that's kind of what we work on. So just to give one last overview, what does that mean for all of our ideas and our projects? So last info session, we got a lot of questions about how do we come up with all our projects and how does the process kind of happen? So it kind of starts out, we have a project idea, we do some research. We all propose ideas in the group, and that's kind of how new projects form. Then you have to look for proposals and for funding to either one, get your idea launched, get it funded. And then we kind of use our external network to match research advisors / industry experts to that project to kind of help us move along. And then another question we got a lot, which was how do we expect to do innovations in space when other companies are trying to do this as well? How can the student group do that? A lot of companies just use analogy to kind of move things forward. And so we are going on a different approach where we look at the fundamental physics of something first and then build it out from there. So a good example is our microgravity experiment. Blue Origin sent us, you'll get an intro about this, But they sent us like a chassis design that weighed 150 grams, right? We're like, okay, that takes up X amount of our payload mass. What can we do to like reduce that? So we reduced the size, we reduced the mass of that by half, just by like taking a step back, looking at our limits, and trying to like do something different. And so then kind of goes into this design and prototype phase, and that creates all our STAC projects. So yeah, now we'll go into who we are.
Hello, so I'm Philip. I'm the engineering director here at STAC, and I'm currently a junior studying mechanical engineering at EECS. So yeah, what is STAC overall? So in short, we're just kind of a passionate student group here who's just really interested in space. And because of that, we want to contribute to the overall body of knowledge that is like space technologies. So that kind of makes us different from the other student groups on campus. As Travis was explaining, we do a bunch of idea generation ourselves. All these come from the students within STAC. And we work on projects that we think can help move the industries forward and kind of contribute to that body of knowledge of space technology. Rather than working on like competition-based teams, which you'll see a lot of other groups on campus. And so on this slide, you see a bunch of keywords that you'll be seeing throughout the presentation. The biggest one kind of being enabling life beyond Earth. So that's one of the ideals of STAC, and you'll kind of see that throughout all the projects that we're doing, that they kind of contribute to this idea of trying to bring life beyond Earth in every one of them. So I'll give it to Olivia.
So, hi, I'm Olivia. I'm a third year EECS major as well as Philip. So who we are. Philip gave a little bit of a background for our general direction and our overall objectives, but we are an engineering-based student group. That doesn't necessarily mean we're limited to engineering, but we do really want to be hands-on, and we're interested and passionate about pushing the frontier of space research. So in addition to who we are, that also includes the people we work with. We are a multi-campus collaborative effort, which means we have partners at UC Davis and UCSB. We also work with the Space Sciences Laboratory up the hill near LBNL. And we have various advisors as well as mentors who help us, and they include professors from Berkeley and other campuses. And our main workspace is in Jacobs Hall. It's the makerspace right across the street, and we will do a lot of our meetings there. Yeah, so we had a lot of visibility this past year. We are a relatively new club, but one of the main things is that we were able to land an article on the Berkeley Engineering Magazine, and for a brief while we were on the berkeley.edu main page, which was pretty cool. That also happened the same month that we launched our crowdfunding campaign, which ended up getting us almost $7,000, and we're using all of that money directly for our projects, and it was very good to start us out. And in addition to that, you'll hear more about these sponsors and partners later, but we have various industry partners who either provide us with free launches or give us mentorship or give us funding, especially on the microgravity payload project or our lunar rover project. So we're going to start out with our first project, and here is Daniel. Or I lied. It's
So, yeah.
Yeah, so as Olivia mentioned, these are our projects. We have a total of 6 of them. And I think that's kind of a cool part about STAC, is that we have such a wide variety of different projects, and you can kind of get your hands on in a whole variety of different areas of space technology. So we have 2 total microgravity experiments, a CubeSat deployer project, an autonomous rover resource collection project, a biosphere where we're trying to help create a system off of Earth, a high-altitude balloon project, and of course, we're also always looking forward to new projects. And that's also something that, as Travis mentioned before, we're always kind of coming up with these new ideas, and as new members, you'll be part of this as well. So we'll start off with the first one with Daniel on the microgravity.
Hi, I'm Daniel. I'm a third-year mechanical engineering student, and I'm also the project lead for the interstellar microgravity experiment, or as we call it in STAC, TIME, because no one wants to say 4 words, 4 very long words. So Time is a scientific payload that's launching aboard a Blue Origin rocket. In the future, we do have a set launch date from them. And for those of you who don't know who Blue Origin is, they're like SpaceX, but instead of getting funded by PayPal money, they're funded by Amazon money. Like, anyways, but their shtick is space tourism. So the flight profile will have 3 minutes of microgravity, and we're basically putting this payload into the spot where the cabin crew would sit on a normal launch. So each of these experiments furthers a goal of enabling life in space. There are 4 experiments on board. We'll talk about one of them specifically, but you can read sort of a brief description of each one. And in like one sentence, you could summarize sort of like the furthering life in space goal as spreading life using tiny waversats propelled by lasers carrying C. elegans that will be manipulated using brushless robot arms. Come talk to me later after the meeting, after the presentation, if you want to learn more about the project. This is a large review of each of the 4 projects. And the one I want to talk about in specific is laser ablation experiment. So it turns out that when you direct a lot of energy at a very small target, that target will heat up and it will ablate. So it will transition directly from a solid to a gas or a solid to a plasma. And the idea behind this experiment is basically to take a laser and shoot it at a representative asteroid sample, in this case basalt, during the microgravity portion of the Blue Origin flight, and observe various effects that this ablation plume has in microgravity, and compare those to ground-based lab tests of the same setup. And some of the reasons that this experiment is important or relevant, rather than just being pretty cool, is that so I'm sure a lot of you have heard about sort of like an existential threat to humanity from asteroids, or rather like really large asteroids striking Earth. So directed energy, or lasers in this case, are one way to deflect those asteroids and mitigate that sort of existential threat. And this is a sort of like small scale first step proof of concept in that you can actually use lasers, directed energy, to generate propulsion, basically. And they're also this is also a proof of concept for using lasers to direct small spacecraft like wafer satellites, as opposed to more conventional chemical propulsion systems. So that's a brief overview of the Time project, but I think I'd like to close by just by providing some motivations as to why you should apply to STAC as compared to like some other engineering club on campus. So I think one of our biggest appeals, especially you might notice in Time, is that we're a very multidisciplinary club. The Time project combines people from a wide spectrum of STEM disciplines, ranging from biology to chemistry to mechanical engineers to EECs. But if you're really interested in just sort of like learning something and that you've never really that you have no idea what it's about, and just sort of like diving in, STAC is the club you want to join. And we have a lot of hands-on work just by nature of our small team size compared to other like larger engineering clubs like CalSol. So you will be doing a lot of the work on a project and calling like this specific part of the project is basically like all like your part. We also have a lot of collaboration with faculty. We're working with a biolab on campus that does research with C. elegans nematode worms, which is something that a lot of other engineering clubs don't do. And we are, as I mentioned before, a small project team, which makes us fairly cozy. And a bit of like sort of motivation as to why like the Time project matters outside of like this grand scope of enabling life beyond Earth. NASA actually has a project proposal, Deepen, where basically the idea is to use directed energy or lasers to propel satellites. And part of the process for getting NASA grants or funding is you have to do small scale proof of concept and approach them with this paperwork and say, hey, like we would like money to do this, and this is what we've done that proves that this is actually a viable idea. Otherwise, NASA will just look at you and say, okay, but where's like the groundwork? And this is sort of part of that goal, as Travis mentioned, of just taking like these small incremental steps to enabling like large future or long-term projects. So that's all for the Time project. Just talk to me after the meeting if you have any more questions.
Cool. We'll go to our other Daniel. Daniel, stop.
Hey, my name is also Daniel, also third year, also Meki, also leading a time project.
They're basically twins. Yeah.
Also, my last name starts with an S. So.
Yeah.
But yeah, so I'm leading the second microgravity experiment. And so I just want to say the reason we're doing 2 experiments is because since we have a small size and mass restraint, so that limits the number of ideas we can do. And since this is sending something up to space, so there's just way too many ideas to explore. So yeah, we want to have multiple projects so that we can explore tons of different ideas. And then also we want to get these time projects to be an annual, yearly project for long-term future of STAC. So something that every year the new team can just do whatever their own microgravity experiments are. And so for my project specifically, it's in the early design idea development phase. So I don't have any concrete experiments in place because I want to both wait for my team of the new people and so we can all have our own input, because then when you have your own input, you'll be way more invested. And then I think just there's a really important part of the project is to get good ideas that could actually help further science or have really good impacts on life in space, life on Earth. So I want to get really strong ideas as experiments first. And so currently some of the things I've been thinking of are bacteria growth in space, because as implications with their virulence and their motility, which could affect long-term life in space. And then also I've been talking to some grad students about fluid mechanics concepts utilizing microgravity, but really it's pretty open. So if you have any ideas or if you just want to get your hands on into the idea stage, and then we'll probably only do ideas for the first month and a half and then start doing design engineering for the rest. So yeah, there's a lot of opportunity here.
Cool. Now we will go to our CubeSat project with Farouk.
So I'm Daniel. No, I'm not Daniel. My name is Varun. That was funny, right? So I'm a mechanical engineer too, and a math major in third year. And so recently, as Travis said, there's it's easier to put stuff into space, but also there's the space industry is moving towards a more modular and compact payload. So you see things like CubeSats, which I'll explain if you guys don't know about it. And but for this project, essentially what we want to do is take it a little bit further with printable circuit board satellites, which are PCB sats. And so this vision came into we kind of did this because of Daniel number 1. The first Daniel you guys talked to, talked about Deep End, where you use lasers to propel small spacecraft to relativistic speeds. So essentially, this is try to get the first framework level of that setup, kind of to get it out in the basically to prove of concept and stuff. And so we're also going to be collaborating with other organizations like UCSB, SSL, which is Space Sciences Laboratory up in the Hill. And so, yeah. And so if you guys, just giving you a little briefer, PCB sats are printable circuit board satellites, as I said. And so the whole point of it is we want to, as you can see by the CAD drawing, it's essentially just literally using a spring system deployer for deploying PCB sats in low Earth orbit. And so that's the CubeSat part, and that comes with its own electronics, and they can be tailored to whatever we might want to be doing. And so, but the printable circuit board satellites, they can also be tailored for whatever application you might want. Like you could have a laser comm system on there for communicating with the CubeSat, imaging systems, 9-axis IMUs, all the cool stuff like that. And so one of the cool applications that we're looking into for this is using this swarm satellite kind of approach with a bunch of PCB satellites for sparse telescopes or detection centers for whatever else you might want to do. But the main crux of the project would be control systems to basically see if we can get this small unit controllable for other applications. And yeah, if you guys have any more questions, talk to me afterwards. and I'd love to talk to you guys. And I'll hand it over to the next person.
Thanks. Okay, now it's Sapir.
Hey, how's it going? I'm Sapir. I'm also a junior studying mechanical engineering, and I'm going to be leading the Autonomous Resource Rover project. So this is in collaboration with NASA Ames, so that's probably one of the coolest parts of this project, that we're working with NASA and they're giving us feedback and all that advising. So what a resource rover is, it's basically just like a regular rover, but we're using it for a different purpose, to extract resources on the moon. So currently most rovers are used for space exploration, but what we're trying to do is take it to the moon and extract resources such as like water, volatiles, and different metals. So that's just like a whole new different scope of space exploration, space like utilization, so commercialization of space. So what we're going to be doing is we're building this thing from scratch. So we're going to be needing mechanical engineers, electrical engineers, and computer science for the autonomous part of this project. So I'm going to pass it on to Malhar to talk more about the autonomous side of it, and yeah, if you're interested in that.
So hey everyone, I'm Malhar. I'm a junior EECS major, so as the pair said, I'll explain to you a bit more about what we're going to do on the autonomous side, as well as the entire design process we're going to go through. So first, in order to train any sort of model, especially if it's a lunar model, you have to be able to recreate a pretty good lunar environment. So in order to do that, it'd be a lot of model creation, people with graphics backgrounds, even those without graphics backgrounds. The Chinese release a lot of information that allows us to create cool models, so we'll be using a lot of that kind of information. The second part of it is once you have a general environment in which you could do a lot of testing, you have to create a model of the actual rover, which would be based off of the mechanical rover that Sapir talked about earlier. Then, in order to train it in this environment, you'd have to create different types of autonomous algorithms. We're going to be using deep Q-learning, but don't be afraid if you haven't worked with Q-learning or anything in deep learning. It's something that you learn along the way as well. The third part of that is everything I've talked about would be done inside this virtual environment. So in order to take it out of that virtual environment and apply it to the actual rover, we'd have to go through that type of iterative testing process. Whereas we need to be able to transfer the algorithm when it worked inside a virtual environment and a virtual moon to an actual rover in a moon-like environment. And then that entire process will have to keep on changing because every time, say you change the rover on the mechanical side, you have to change the entire model as well, because it's always going to adjust for different ways the rover functions, moves, as well as collects information inside a simulated environment. So if that appeals to you in any way on more of the CS side, then also feel free to talk to Sapir after.
Sounds good to me. So we have like a demo of what Malhar was talking about with like sort of like the virtual moon like simulation and like the CAD of the rover itself. So here is like an example of the rover with like a reward function. So it's trying to navigate this select path in the most efficient way while also picking up as many resources as possible. So like we would have obviously a more complex extraction method, but this kind of shows like what possibly could happen on the moon with the technology that we have available and like with NASA's help, obviously. So if you have any other questions, just feel free to talk to me after. Yeah, thanks.
Actually, when we went to the NASA, like the people we were meeting with, we had to like teach them about the whole like autonomous side. It was kind of fun. Malhar spent like a good 30 minutes explaining. Yeah. Okay, so now we'll have Will talk about our biosphere project. And you can thank Will for the pizza, by the way, because he went out all the way to Costco.
All the way to Costco. They almost didn't let me. The guy like shut me down, and I was like, "No, please, we need a lot of pizza." My name is Will. I am a second year, and I am not an engineer. Actually, I'm a molecular environmental biologist, but I do like engineering, and I'm in charge of the biosphere project as of right now, which is going to be a goal for habitation. I think it's the coolest thing ever. It's kind of like building a greenhouse, but the goal is to make it something that could be really useful for astronauts and people who are settling on foreign planets through agriculture, which could support food or pharmaceuticals or biofuels and more. And this is just like also a point of sanity for people who are probably going to spend the rest of their life not on this planet. I think one of the major things that defines the biosphere is the fact that the ecosystem is going to be self-sustainable. I mean, like any ecosystem should be. but we humans haven't really been good at creating that. And one of the things that we think will be best for supporting it will be a really complex control system. I don't know if any of you know about control systems in mechie and engineering, and this is something that is probably going to be like our most complicated part of the project, but also one of the most that would gain us success and or fame for it. And we want to be able to design a software system that would be able to support and respond to this environment and ecosystem to keep it sustainable without having to like have someone sitting in NASA Ames like controlling it all the time, because it takes like 15 minutes to send a signal to Mars. And that's one of the bigger things. We really want to focus on iterative design, like you heard about modulation earlier on. It's a really big thing, so that way we could send like 10 units out right now to build something small, and then in the future be able to expand it to more. And also that means in our stage right now that we could build like one and show that it could fail and learn and work, instead of trying to build like one big unit and have it collapse or something. But I think this is super cool. This project touches on like a lot of different aspects about chemistry, ecology, and of course like all the backgrounds of engineering that this club covers, and it's quite diverse and cool, and I'm really excited for it. Once again, my name is Will, and like if you have any questions about this or would like to help out, come on after and talk to me. Thank you.
Cool. And now we'll have like our last project, and Victoria will talk about it.
Hi. My name is Victoria. I'm also a third year. I'm also studying mechanical engineering. So we're doing a project on high altitude balloons. And so if you don't know what high altitude balloons are, they're a really low cost, like effective, very hobbyist way to launch payloads into near space. And they're unmanned balloons that are usually filled with helium or hydrogen that can reach extremely high altitudes near space. A lot of what they're used for is to gather data on kind of atmospheric or like climate change. They're also being used for kind of space travel. They're trying both unmanned and manned missions using high altitude balloons. Google is using a project called LoonX to like expand like Wi-Fi to rural areas, places where they may not usually have internet connectivity. Essentially like the poor man's space program. So what STAC is doing is we're developing a standard launch pad platform for high altitude balloons so that we can send low cost scientific experiments into near space. And so a lot of the work that we're doing is developing a repeatable launch to put our own experiments onto. And so we have a lot of different variety of experiment ideas, but so far we're focusing our efforts on standardizing payload and launch so we can repeat experiments. And so the first semester will be spent building the first balloon launch, and then afterwards we'll start working on standardizing payloads and then partnering with other professors and labs on campus and industry like NASA. We've actually had some professors that are interested in using our, once we actually build it, high altitude balloon platform for like imaging clouds.
Yeah, it's like imaging like the candy like cotton candy like clouds. I don't know if people do that, but
yeah, so I mean there's a lot of clouds. They want pictures of clouds and we can help them. So yeah, it's a really, like a lot of these projects have been pretty interdisciplinary. We're looking for a lot of different backgrounds, you know, aerospace, mechie, CS, physics, EECS, yeah, anything. That was not everything, but yeah. So we're definitely, you know, open to a lot of different majors. You don't have to specifically, like for a lot of these projects, you don't have to have specific knowledge that like applies directly to your major. It's more about like what you're willing to bring to the project, especially because a lot of them are starting so off the ground. So yeah.
Cool. Now we'll go back to Malhar for talking about like a little bit about the external thing that we kind of mentioned in the beginning.
Hello, everyone, again. So I'm Mohar. I'm also the external VP. So a lot of what I do is just talk to people outside of STAC, as well as people in the school, in industry, doing cool shit, and seeing how we could learn from them, as well as how we could work with them. So one of the ways we do that is working with other labs. So here are a few examples, and I can tell you a few examples of what we do within each of them. For UCSB's Deep Space, they actually help make the PCB sats that we mentioned earlier and to do a lot of our experimentation. For the laser thermal lab, if you're working with lasers, you know what you need? A lot of testing equipment for said lasers, or exactly how to use those lasers in certain environments, which means labs dedicated to specific types of experiments that we want to do are best catered towards us, which is why we end up reaching out to them. So that's just like the general gauge of labs in general, and these are just a few of what we're currently reaching out to. As we take on more projects and get different types of focuses, then we'll bring on even more and have a bigger variety, because my goal is just to provide all of you as engineering people within STAC with the best resources you can get. So you can focus on building cool stuff, and I can focus on getting you that cool stuff to build cool stuff. All right, second point, sponsors. You may have seen a few of these, you may have not. So the few you may know is, say for example, Blue Origin. But the way we got the Blue Origin launch in the first place that we talked about in the Time Project is through the Dense Space Conference. So Olivia and Travis, I believe, actually proposed a paper there, and they won a competition which gave them the ability to send a payload on that Blue Origin launch, and then ended up being a major sponsor for a lot of the work we ended up doing. For NASA Ames, as Sapir mentioned earlier, they're the people that are working with us most for the rover, giving us not only a bit of money, but a lot of mentorship as well as expertise in the area. Although we think we know a lot about space, we also have a lot to learn from the people around us because they've all been dealing with this industry for a really long time. The other people mentioned here, KLA Tenker, Pear, and the Berkeley Student Tech Fund, help give us money so we can keep on buying the necessary tools we need, as well as have the necessary space, licenses, and whatever else you need in terms of materials. The third major component is advisors. So I gave you a bit about things like workspace, and then I told you a bit more about the actual physical resources we're getting. Advisors function as that third portion, giving us the actual advice on how to operate within a research portion of the industry, as well as how to operate as a space company. One thing Travis and I did this past summer is when he mentioned that giant list of companies at the beginning, we met with 20 to 25% of them over the course of the summer. Just because, like, why not learn more and see what we can learn from people that have been in the industry for 20 to 25 years. We ended up finding some really cool people, and we brought them on as advisors. For example, the individual we have at Founders Fund, which is a venture capital firm, he was an early employee at SpaceX. And his other partners now went on to make their own venture capital firm that focuses on SpaceX investments. RBC Signals, they work on RF communication between satellites, which means now we have advice from someone that's actually not just, say, a business person, but someone that has engineering abilities as well. So they can kind of teach you that all the cool stuff that you would build, like regardless of STAC, you can take beyond just, say, school, and you can apply it beyond that. The third part, B Partners, very similar to Founders Fund and Kickstarter as well. They both help us a lot with funding as well as advice to make sure we're on the right track, because that's the point of an advisor, to make sure you don't just lollygag around everywhere and make sure you have a focus in what you want to do. So this is just what I'm doing, and I really want to bring on another person to help me, which is why it says down here I'm looking for an outreach director. So if anything I just said earlier was of interest to you, whether it's talking to all these cool people, like I think I've talked to about 200 people over the course of the summer with Travis and Olivia. If that sounds cool, feel free to hit me up after, as well as if you're interested in just reaching out and learning more about the industry as a whole, as well as applying engineering to it.
Cool. And then like we're almost done. We'll just talk a bit about like the recruitment side of things. Yeah.
So we are mainly looking for project members for the recruitment phase. So if any of the projects like sound interesting to you, please do apply. And then on the application, it says like, oh, what are your like most interested projects? So everything in blue is stuff that we need to fill, but again, an emphasis on project members. We do have some engineering experts that we're looking for, also a co-AI lead for the resource rover. As Malhar mentioned, an outreach coordinator or director and a financial director. So this, in addition to like hearing about all of the engineering work that we do, we also actually have fun. Like we are a family. I posted this on my Facebook when like advertising this event. They like STAC really has become my family. There's us at a barbecue. There's us at NASA Ames visiting due to like the Resource Rover partnership. We got a tour of like 3 of the NASA Ames labs, and we went this past like a month ago. We also have people going to conferences. So there's Will and I at the Dent conference, and like we got flown out there. We got to spend like a whole like half a week there to meet really cool people. And then there's Varun,
That's at the
Travis,
new
and
space
Mohar at like different external events. So if you want to work on really cool things and be hands-on with engineering or science in general, but also want a community that you can just hang out with, you should join STAC. So like I said earlier, we're mainly looking for project members, and project members, you can either be part of one or multiple projects, and then you're responsible for researching, prototyping, designing, and like sub-tasks in that project assigned to you by the project lead. Project leads are people who presented, they are responsible for the day-to-day operations and like delegation of that project. We also have the development side, so that's Malhar, the outreach director, the financial director, anything non-engineering, and Camille as well, anything that involves STAC development as a whole. And then finally, the engineering experts. They're just people who come and hop around in the projects and give advice. These people, we would prefer to have a lot of experience in the field that they're in. And generally, if you're applying for if you're applying to join this semester, we would say wait to apply as a project member first, and then you can become an expert later.
Okay, so after all that great information, I know you're all dying. How do I get in? What do I do next? So the first thing is you should fill out that bit.ly that says you're here /stack-info, your attendance, because that'll be a plus points on your application. And then the application is right there, stack.berkeley.edu/join. And it's a type form, and it's very friendly, very straightforward. The application is due by the end of Friday. So today's Wednesday. You have 2 days to fill it out. The interviews we'll be deciding who gets an interview on Saturday. You'll know if you have an interview by Saturday, by the end of Saturday, and then you'll actually have your interview on Sunday between 9 a.m. and 5 p.m. And then you'll know if you're in or not by Tuesday. So it's all up there. I just repeated it for you. Let me know if you have any questions about that.
Yeah, and it's Friday, 9 to 8, sorry. Because today, or tomorrow will be the 7th, but it's Friday is when it's due. So that's kind of like the general idea of like the recruitment phase, so you guys get all the dates and we'll hear from us really soon. So the attendance link is both here and there. I just want to like say a few final remarks before we like close it. You guys get pizza, whatever's left, and then talk to the members. But I think like it's pretty clear that we're trying to do projects that kind of get humanity one step closer to some really long-term goal. Because like a lot of people just assume things get worked on. So like if you hear about like protecting the Earth from an asteroid, you may assume like there's a NASA center set up for that. Well, maybe there's actually not. So you have to like look at these assumptions people make and then see like, is there something we can kind of do to help out along this path? And so that's kind of like what each of these projects entails. And so once we do find that project, we end up doing like a research-based project on that. So everything you kind of saw was research-based. And so it has some scientific implication, which then leads to like us going to conferences and publishing papers with all our names on it. And then on top of that, like we get to launch things into space, which is like so great and like so much fun, because on the days of the launch, that'll just be so exciting. Just like say, wow, we worked on that and it went to space. So I think these are really great things to kind of look forward to, and we really are excited you guys are all here. So thanks.